Welcome back, guys. In this series we will continue with the section or the subunit of sets, Venn diagrams and number types. In this particular video we will be looking at Venn diagrams, having already discussed the idea of sets and different types of sets. Okay, so let's begin. And by the way, this is going to still be revolving around the eWorkbook number 4, so please check down in the comment section for this eWorkbook. Okay, so let's begin. We're discussing Venn diagrams, right, and how Venn diagrams find their use in representing sets. Okay, so Venn diagrams are a way of visually representing sets and their subsets. Okay, it's a very compact way of looking at all sets and their subsets within one single space. Okay, so as I've said here, a Venn diagram offers a compact and efficient means of representing or visualizing sets and their subset. Okay, for example, when we represent sets and their subsets using Venn diagrams, we have usually we use a rectangle represented by U, followed by the sets or the subsets of U inside it, as shown using circles like that. In this case, U is called the universal set, and A and B are the subsets of the universal set. So what do we mean by this? Let's just look at some examples. Okay, so the universal set, by the way, is defined as the set that contains all possible outcomes in a given scenario, right? So if we are going to consider different types of sets, they must be coming from a possible scenario, a possible number of elements within a set. I'm going to explain this as we move on. So in short, the set that contains all possible elements under consideration and from which all the other subsets are derived or taken from is what we refer to as the universal set. Okay? For example, the set of all letters in the English alphabet is the universal set from where we get our vowels and also from where we take our consonants. Here is the example. So these are the letters or the letters in the English alphabet. Okay, there are 26 of them, and from these we can set a universal set U. So set U represents all the letters in the alphabet. Then in that case, set C, which will be inside the universal set, will be the set of consonants, and V will be the set of the vowels. Okay. Here is another universal set, another example of a universal set. The set of all living things can be considered as a universal set. Okay, so in this universal set we have animals, plants, fungi, and small microbes. All these are subsets of all living things. So we refer to them as the subsets within the universal set. We can represent this on a Venn diagram as shown. So there is the living things represented by U, and we can place in the animals in their own set, plants in their own subset, fungi in their own subset, as well as the microbes like that. So this would be a Venn diagram that represents living things with all the possible subsets of the living things. All right, I think I have another example of this. We can look at the subset of integers. So integers can be considered as its own universal set, and so within integers represented inside that rectangle, we can have negative numbers, positive numbers, and of course the zero. All right, so the circles represent the subsets of the universal set that contains only integers. Of course, within this set we could also have odd and even numbers as separate subsets of integers. Okay, all right, let's move on. Now we start defining different types of set, and one of them is the complement of a set. Okay, so if a set is given by A, if we have a set A, then the complement set is defined as all the elements that are not inside A. So, as we've written here, the complement of a set A, denoted by that A with an apostrophe on it, is called the complement of set A, and it is the set of all elements in the universal set that are not in A. So everything in the universal set that is not inside set A is referred to as the complement of set A, and I'm giving examples of this. So if that's the universal set, then that, what I've drawn there, that circle, the yellow circle there, represents everything that is in set A. In which case, everything that is not in set A would be outside that circle. It's inside the universal set, but it is outside the circle. And we can represent that this way. So the complement of the set would then be represented like that. Okay? So it refers to all the elements. So the yellow, the area shaded yellow represents everything that is outside of the circle, outside of A. And that is called the complement of the set. Let's look at an example of the complement of a set. Okay? Below is a set of solids. Okay? Solid shapes, basically. All right? There is a set A which represent all prisms. Okay? Suppose that set A is the set of prisms within this universal set here. Suggest elements of the universal set that do not belong in set A. That means that are in the set A complement, meaning they do not belong in the set A. Set A being the set of prisms. So which elements in here are not prisms? Okay? If set A represent prisms, then which are the prisms? Well, this here, this is a triangular based prism, right here, the one in blue there, triangular based prism. Okay, we have a rectangular based prism in purple, is that pink if you like, and we have a square based prism which is in orange. And if I look carefully, there is one more prism here which is a circular based prism, also called a cylinder. That's also a prism, and I can't see any other prism. So anything else that is not a prism must be in the set A complement. And that refers to, I think the first one there is that yellow. That is a pyramid, a square-based pyramid. We also have down there a triangular-based pyramid. Then we have the sphere there is not a prism, so it is in the set A complement. And the cone, which is a circular-based pyramid, is also in the set A prime. Okay? So we have indicated all the elements that are not in the set A. Okay, elements in the universal set that do not belong to the set of prism are the ones that we have ticked there. Okay, let's move on. The intersection of sets. We want to define what the intersection of sets are. Okay, so this is how we represent the intersection of two sets A and B. So how do we define the intersection set? It is the set of all elements that you will find in A and also in B. Notice I've put and here, and this is important. Okay, so it has to be, so for an element to be in the intersection of a set, it must be a member of set A as well as a member of set B. Okay, it must be an element of set A and an element of set B for it to be in the intersection. Here is a diagram that we draw to represent intersection. So if that's set A and the other one is set B, then the intersection refers to the region between. So we are going to shade that in yellow, the region between A and B, where A, set A and set B intersect. It is called the intersection of set A and set B. All right, let's look at an example of the intersection of a set. The set A, B, and A, B, and U are such that the set U, which is the universal set, contains all integers lying between 0 and 8. I should have indicated inclusive, meaning 0 and 8 are also included. So that, let that be the universal set. So all integers that lie between 0 and 8 inclusive. That's 0, 1, 2, 3, 4, 5, 6, 7, and 8. And let set A be the set of all prime numbers that fall between 0 and 8. Let set B be the set of odd numbers that lie between 0 and 8. Okay? The question is for us to list the elements of the set A intersection B. Well, to answer that question, the first thing we want to do, of course, is to list all the elements of U, A, and B. Now, to list that, what do we do? The set of U is given there, 0, 1, 2, 3, 4, 5, 6, 7, and 8. The set of prime numbers, that is set A, must contain only 2 prime numbers. Here are 2, 3, 5, and 7. So the set of prime numbers is that, set A. And set B is referring to the odd numbers between 0 and 8, and that would have to be 1, 3, 5, and 7. So set B is 1, 3, 5, and 7. And so from here, we will be able to determine the intersection. So if we draw the Venn diagram there, including A and B there, then we know that the region we are searching for is the intersection of those 2 circles, all right, which we have shaded there. So if we are going to find elements of that intersection, it means we look at set A and set B, and we find the elements that are both in set A as well as in set B. And if you check that carefully, you can see that 3 is one of them. 3 is there, and it is also on the other side in set B. So we can indicate 3 as one of the elements. The next one there, C, is a 5. 5 is in set A, and it is also in set B, as you can see. And so 5 is also an element of the intersection of A and B. Lastly, we have a 7 there. And 7 is in A and it is also in B. So 7 is an element of the intersection set. So we can conclude that the intersection set contains, if we were to list these members of this set, we will say A intersection B contains 3, 5, and 7 as the elements. By the way, if somebody asks us for the cardinality of the set, we can quickly write that. The cardinality of the set refers to n of A intersection B. That means the number of elements in A intersection B. I think we just need to do this to keep track of what we have discussed earlier. So this would be 3. Similarly, if we were asked for the number of subsets, that means the power of the set A intersection B. We can list the elements, but if we are looking for the number of elements in the power set, then that is going to be 2 to the power of 3, 2 to the power of number of elements, and that's going to be 8. So we expect to find 8 subsets of the set A intersection B. If somebody was asking us to find the number of subsets in this set, then this is how we would find it. It is also possible to list the subsets of the set A intersection B and the subset. If we can list all of them, that would give us what we call the power of the set. Okay, let's continue with this. Now, so this, as we've seen, these are the elements of the set A intersection B. We could find the complement of this set. The complement of the set A intersection B must be everything that is outside this region A intersection B. Okay, and we would represent that way. Okay, so everything that is outside the set of the intersection, that is outside the intersection region, would be the set of into bracket A intersection B complement. All right, and what would that represent? Now, if you check that carefully, it means if we put everything in there, so we will skip only 3, 5, and 7. So go and get rid of 3, 5, and 7 here, and whatever remains has to be in the complement set of A intersection B. Okay, so I'm putting them in there, and therefore we can say that A intersection B complement must be 0, 1, 2, 4, 6, and 8. Those are all the numbers that do not fall in the intersection set. I hope this is clear, and let's move on. All right, next let's look at what we mean by mutually exclusive sets, or sometimes called disjoint sets. Okay, so by definition, two sets are disjoint if they do not have any intersection. So disjoint sets are sets that do not and cannot have common or shared elements. Okay, so these disjoint sets do not intersect, which is to say also that the number of elements in the intersection must be 0 since they do not intersect. Like this. So if we have a set A and set B, so that there is no point where the two sets intersect. So if we have that scenario there, then this would be, we would say that A and B are disjoint, okay? Or they are mutually, A is mutually exclusive to B. A and B are mutually exclusive, all right? Disjoint of a set. So for disjoint set, as I said earlier, the intersection must have completely no element. So this is a null set. In the case of a disjoint set, A intersection B is null, which is to say there are no elements in the set. Okay, we can use common English expressions to understand what disjoint of a set is. Let's look at an example. In the set of integers, a number can be either even or odd, but not both. So we cannot have a number that is both even and odd. It's either in the subset of odd numbers, or it is in the subset of even numbers, or it is a 0, but it cannot be both in the even numbers and in the odd numbers. And that is to say that A intersection B, so if this is A and that is B, then A intersection B is 0. There is no number that falls in both subsets. Okay, so A intersection B is a null set. So in English words, in English expression, we say we are either keeping the egg or making an omelette from it, but we cannot have both. Another way to say this is you can have your cake, you can't have your cake and eat it. So if you either have the cake or you have eaten it, you can't be having it while at the same time you've eaten it, right? So this is a good way of understanding what we mean by a disjoint sets. We move on. The union of sets. So the set A union B is the set of all elements present in A or present in B or present in both A and B. Okay, that is the union of a set, and this is how we represent this on a Venn diagram. So that is A, and we have a set B, and so the union of the set would be referring to all the yellow shaded parts. So either it is in A, or it is in B, or it is in both A and B, like that. So that is the union of set A and set B. We can also draw the complement of this set. The complement would mean everything outside this yellow section. That means in the universal set, of course, but outside the yellow section, and we would represent that like that. So this is the complement of A union B. Let's look at some examples. Okay, in the set U, A, and B, from the previous example, the set U was given by that, the set B, set U, set A was set of primes, and set B was the set of odd numbers. If you remember the previous example that we gave, we're going to use this to try and look at all the stuff, all the types of sets we've looked at so far. All right, what is the question for us? That is what we would refer to as the union of set A and B. So if we put in all the elements in there, then this is what we had. We had a 0. 0 is outside of A and B. All right. 1 is in set B, but not in set A, so it will be in this region here. I think 2 is in set A, but not in set B, so it falls in that region. And otherwise, the rest of the elements are outside both set A and set B. They are neither odd numbers nor prime numbers. Okay? And so, if somebody was to ask the set of A union B, then that must be everything inside that yellow shaded region. So that's 1, 2, 3, 5, and 7. But we could also find the complement of that set. So everything outside that yellow shaded region. So the set of A union B, everything complement would be given by the stuff that is outside. So that means now the part that is shaded in yellow there, and you can see it's 0, 4, 6, and 8, like that. So that is A union B complement, right? Let me know if you have issues with this, but otherwise I think this is plain straightforward. Either way, let me know if you need further clarification. Next, let's look at the difference of sets. Okay, this can sometimes confuse students. So what do we mean by the difference of sets? We can have the difference of set A and B, or the difference of set B and A. The difference of set A and B means A minus B, and the difference of set B and A is B minus A. So by definition, the difference of two sets A and B is the set of all elements that are present in A but not in B. So if the elements are in A but not in B, that is called the difference set, and we're going to see this quickly. So we have our set A and set B. All right. That region that is now shaded refers to all the elements that are in set A but are not in set B. Elements in this region are in set A and B. So if we want elements that are only in set A but are not in set B, that it must be that moon crescent shaped shaded region there. So that would be A intersection B complement. That means A intersecting with everything that is outside of B, right? So A intersection B complement is the set of all elements that are in A but not in B. So you could read this as A and not B. Okay, that there. We can read it as A and not B. Remember, the intersection there is read as and. So A and not B. That is what we've shaded there. Similarly, we can find the set of elements in not in A but B. You can also read this as in B but not in A. Okay, or B and not in A. B intersection A complement. So that is represented by that. Let's look at an example of a solved problem. So the solved problem here now should involve all the areas that we've discussed so far. So given that the set U is that 0 to 8, set A is 1, 2, 3, 4, and set B is 2, 3, 5, and 7. Okay. Find the intersection set of A and B. Also find the union set A union B. Find the difference set in B and not A, and the union set, the difference set in A but not in B. Okay, we want to find this. So to do so, of course, the first thing is to draw the Venn diagram. So I have my Venn diagram here, A and B, and I slot in the values of elements in all the three regions. So we start with the intersection. We can see, if we look at A and B, the elements that are in A and also in B, I can see there is a 2 there, there is a 3, I think they're just those two, 2 and 3, and so we put 2 and 3. Then there are those elements that now fall inside A. So A has got 1, 2, 3, 4. So 1 and 4 must now fall here since we already have 2 and 3. So we can put 1 and 4 there. On the other side, we can put a 5 and a 7. And whatever remains goes outside A and B, but still within the universal set. So what does that give us? 0, 6, and 8. I hope you can do this easily. And now we can go ahead and answer the questions we are being asked for. What is the set A intersection B? So write out the set A intersection B. Okay, that's part A, that's shaded in green. So if we're going to find A intersection B, we know that that is the region where circle A intersects with circle B. I'm shading it now in yellow. That represents A intersection B. And we can now list out the set A intersection B as shown below. Okay? Similarly, let's go to part B. Now I'm shading part B. We are looking for the union, A union B. So A union B, once again, looking at that Venn diagram, A union B would refer to any element that is in A or B or both. So it's either in A or it is in B or it is in both A and B, like that. And to do so, that means I shade all the region of A and B and the intersection. And so we can list the element in the set A union B as given. All right, notice we leave out 0, 8, and 6 because they do not fall inside A or B or the intersection. Okay, what about part C? We want to find the elements that fall in B but not in A. So they are inside B, but they are not inside A. So inside B, but not A, that would be this moon crescent region here. I will shade that. Okay, that is the set B, not A. So in B, but not in A. Or not in A and in B. Okay, and so that set contains 5 and 7. We can list that. The set A complement intersection B contains the elements 5 and 7. Let's move on. Part D. Now we want elements that are in set A but not in set B. So if you go by, if you catch the wave, then that means now we are talking about elements in this crescent here but which are not in B. So if we shade that region there, we can see that the elements in set A intersection B complement must contain 1 and 4 only. Yes? Let's move on. Here is an investigative task that helps us understand a few things. The same set we have there are shown on the Venn diagram. So we have this set shown on the Venn diagram. One more time. It's basically the same set we've been looking at, but this is now investigative. Shade the relevant regions of the Venn diagram, okay, and list the elements in the set. So I'm going to do the first one, and then you'll do the second one. All right, so shade the region A complement intersection B complement. So that means it should not be in A. So we are shading everything outside A, and then, so everything outside A. Okay, so that is the set of A complement. Similarly, if we shade everything outside B, there is that, and then B complement would be the yellow region. Okay, so now A complement intersection B complement must contain both, like that. So the outside of A intersecting with the outside of B must be the shaded region that is shaded in yellow. All right, now if you look at that region, it is also the same as, okay, so A complement intersection B complement contains 0, 6, and 8. But you should also notice that the set of A union B complement, so A union B would be the dark region, complement means outside it, is also the same thing. So we can conclude that A complement intersection B complement is the same thing as A union B, or everything into bracket, complement. Okay, so that is a result that I expect you to be able to see easily by just shading out the regions like that. Okay, so what you're seeing here is you can refer to it as A complement intersection B complement, or you can refer to it as into bracket A union B complement. Right? Means the same thing. It means that if you have A union B with a complement outside, you can distribute the complement to the A and to the B, but if you do so, then the union flips and becomes an intersection like that. So if you open the bracket so that the complement sign goes to A and to B, then the union sign is going to flip and become an intersection like that. So keep that in mind. It becomes useful in the future. The next one that I want you to try is to see the relationship between, so you will draw a diagram just like this, the set A complement union B complement, and we want to compare that with A union B, everything, A intersection B, everything complement, right? So try that out and let's see what you get. So you can pause the video and try it out. All right, now if you've done this correctly, then what you should have noticed is that one, we've said that A complement intersection B complement is equivalent to into bracket A union B complement, and we found that to be 0, 6, and 8, contained the elements 0, 6, and 8. You should also, and that's what we show here in the diagram, looks like this. If you do this, if you did the second one, then you should have noticed that the set A intersection B, everything complement, must be the same thing as set A complement union B complement. That is to say that if you open the bracket with an intersection inside, if you open the bracket so that you distribute the complement there to A and to B, then the union symbol is going to flip and become, the intersection symbol will flip and become a union symbol like that. And if you check on the diagram, the elements are going to be that. Okay? So, A union B, A intersection B, which we know is this region. So if we say complement, then that means we are looking at everything outside this region. It turns out to be the same as A complement union B complement. So outside A together with outside B. So everything outside A add to everything outside B. Okay? And that gives us that set of elements. Please be sure you understand this in case somebody brings it out in a test or in an examination. All right, we can move on. And here are some problems involving Venn diagrams. I have solved some of them, and I have left some of them for you to solve. Let's hear what you have. Let me know what you get, and we can discuss it in the comment section or when you contact me directly. So the Venn diagram, this is problem number 1. The Venn diagram illustrates the number of students in a particular class who study both French and Spanish. So we're going to represent the subset F, French with F and Spanish with the letter S. Determine the number of students in the class. That's part A. Part B says determine the students who study both subjects. That means they study French and Spanish. Then determine the number of students who study at least one subject. That means they study either one or both. Okay? And lastly, the students who study only Spanish. So this is referring to stuff that we've discussed previously, but let's see how we interpret this. So determine the number of students in the class. So clearly this is referring to the universal set, okay? Because whatever we are talking about involves students in a particular class. So whatever we choose is going to come from this class, so that represents our universal set. So we are basically looking for the universal set, which is the whole thing, whole stuff inside that rectangle, which I've now shaded. And now we look at the number of students in those inside the shaded region. And if you check that carefully, it means we are adding. We have 12 plus 4 plus that is 17 plus 1, which is 18. So we can say that the number of elements in the universal set, the number of students refers to the number of elements in the universal set, and that is 18. I hope that is clear. So if we are saying that the number of students in the class, you should interpret that as the universal set. The number of students who study both subjects, that would be the intersection. That means they study French and they study Spanish, so they must fall in the intersection region. So we can represent that. That is clearly 2 students who study both French and Spanish. So we can say that the number of elements in F intersection S is 2. There are 2 students that study both French and Spanish. The number of students who study at least one subject, that is interpreted as the union set. So they are either studying French or they are studying Spanish, or they are studying both, because at least means one or more, so they can be studying 2 subjects, right? And that means the number of students who study at least one of the subjects has to be F union S. I hope this is really making sense, so we'll remove that, and F union S is shading all that region inside F and S like that. And if we add the elements in there, we get that the number of elements in F union S is 17. Okay, only one student is not studying French or Spanish. All right. Part D, determine the number of students who study only Spanish. So how many students study only Spanish? So that means they study Spanish but not French. So S but not F would be S intersection F complement. In S, not in F. Okay, so that is S intersection F complement. What is S intersection F complement? That would be the moon shape, the crescent shape around this. Let's see. So that is referring to that region there. And as you can see, there are 12 students in that region. So we can say the number of students in F complement intersection S. That is to say, not in French, but in Spanish, that has to be 12 students, like that. I hope this is making sense. This is a question that I want you to try out. Or did I solve it? Yes, I have solved this one. You can pause the video and try it out yourself before you check my solution. Please pause the video and try out this one. In a survey at a resort, people were asked whether they were sailing, they went sailing, or they went fishing. Again, we are using letter S and letter F to represent sailing and fishing. Okay, so during their stay, they could either go sailing, or they could go fishing, or they could do both. Use the Venn diagram to determine the number of people. Okay, so the Venn diagram is given here. Use that to determine the number of people in the survey. So the number of people in the survey must be the universal set. So what's the number of people in that universal set? To determine who did both activities. So if they did both activities, that means they went surfing and they went sailing and they went fishing. Okay, so where does that belong? And the next one there is the number of guests who did neither activity. They neither went sailing nor fishing. They didn't do anything. Okay, they were guests at the resort club, but they didn't do any of the two activities. How many are those? And how many of them did exactly one activity? Okay, let's see that now, assuming that you have tried it out. So let's see if you got the same answers as me. So the first one is the number of students, or the number of guests in the survey. That must be referring to the universal set. And to get that, we have to shade the whole rectangle there, like that. And we count all guests that are in there. And so it's 1 plus 27 plus 9 plus 15. And if we count all that, we should find the universal set contains 52 guests. Right? Next, how many guests did both activities? If they did both activities, that means they went sailing and they also went fishing. Right? If you check that out, that should be the region I'm shading now. It is the intersection set, and that is 9. So we can say that the number of guests that went sailing and fishing, that is N, the number of elements in the set S intersection F, is 9. Okay, next, who did neither activity? How many guests did not do any of the activities? Clearly, we are talking about the elements outside that set, and as you can see, so anything outside the circles, so the part that is shaded in yellow, and we can see there is just one student who is in the set of S union F complement. Okay, neither went surfing nor fishing. So that's just one guest. How many guests did exactly one activity? So if they did only one activity, 9 cannot be in the set. So it must be this set here and that set here. So this is the set of guests who went sailing but not fishing. And this is the guests who went fishing but not sailing. So how many did exactly one activity? It must be 27 plus 15 there. We can represent this way. We would have to shade that region. Those are the members that did exactly one activity. And that is going to be 42. When you add the two, when you add those two numbers, you should get 42. Okay, I hope you got that right. Here is another one. This one I have not solved, so this is related to chemistry and physics, so I have put those animations there. In a class of 30 students, 19 study physics, 17 study chemistry, and 15 students study both of these subjects. Display this information on a Venn diagram, hence determine the number of students who study both subjects. Find the number of students that study at least one of the subjects, and then determine the number of students that study physics but not chemistry. Part D requires you to find the number of students that study exactly one of the subjects, and Part E, you should determine the number of students that study neither of the two subjects. Okay, so this I have not even tried. Please try it out and let's see what you get. Send your comments, send your solutions if you like, and we can take a look at them. Here is another one. This is usually for students who've understood the basic material and so want to go a bit further. I believe I've solved this one. In a circle of music lovers, 14 people play the piano or violin. 8 people are piano players and 5 people play both instruments. So we know 5 of them play both. Find the number of violin players. How many students in how many people in this circle of music lovers play only violin or play violin? All right, so of course to answer this question we start by drawing the Venn diagram and place the cardinalities. So what we have been given here are cardinalities, number of people in each set. All right, so here is the set of piano players. I'm representing that using letter P there. And this is the set or the subset of violin players. Okay, so looking at the question, we always start by looking for the intersection. So we are told there, if you read carefully, 5 people play both instruments. So that implies that the yellow or the orange, dark orange section there refers to the people who play both instruments. So we can place 5 there. Okay. Next, we are also told that 8 people are piano players. So who are the piano players? Piano player is this first circle there. That's the first set. Okay. 8 people are piano players. So if the total there inside that circle is 8 and we already have 5 in there, then that leaves us with only 3 players who 3 who play piano but not the violin. Okay. All right. But then we are told that 14, we can remove that, and then 14 people play the piano or violin. 14 people play the piano or the violin. Okay, so which is to say we already have 8 people playing piano. All right, so 14 out of 14, how many do we still have that will play the violin? And if we check that carefully, we need to add, this is 8, what we add to 8 to get 14, and that should be, that region there should be, that is 14. So what is remaining for us to have 14? It has to be 6. All right, and therefore it is now possible for us to answer the question, find the number of violin players. Violin players must be this subset of V, right? And that is 11. So we can say that the number of music lovers that play violin must be 11. So therefore, number of elements in the set V is 11. Okay, here's another question. I want you to pause the video and try out this question and then check my solution. So a survey is made of the investments of the members of a club. All of the 133 members own at least one type of share. 96 members owning mining shares, 70 having oil shares, and 66 members having industrial shares. Of those who own mining shares, 40 also own oil shares and 45 also own industrial shares, while the other members who own oil shares and industrial shares is 28. How many members of the club own all three types of shares? Okay, I want you to pause the video and try this question out. What I need to tell you is that this set here, this particular question, the Venn diagram has got three subsets, not just two. Okay, so one subset is for mining, one subset is for oil shares, and one subset is for industrial shares. So if you do that, and then you can distribute the numbers accordingly to get your answer. All right, assuming you've done it, let's go and see the solution. Please remember to try it before you check the solution, right? But assuming you've done it, let's go ahead and check the solution. So before I go ahead, I'm just going to list these values here. So all members, all of the 133 members own at least one share. So there are 133 members of the club, so that is the universal set. So we can start by saying that the universal set contains 133 members. All right, and then it says that out of those 133, 96 members own mining shares. So we can say that the number of elements in set M, okay, those who own mining, M for mining shares, is 96. I'm going to represent oil shares with the letter L as opposed to letter O, but you can use your own letter, it doesn't really matter. It says 70 have oil shares, so we can say the number of elements or the cardinality of L for oil is 70, and the cardinality for industrial shares is 66, so the number of elements in I for industrial shares is 66. Any other information? We are also told that of those who own mining shares, 40 also own oil shares. That is to say that M mining intersection L, these are those who own mining and also oil shares, right? So we can say the set of elements in M intersection L, okay? The intersection of mining and oil is 40. So there are 40 members who own both mining and oil shares, and there are 45 members who own mining and industrial shares. So M intersection I is 45. Okay. Lastly, 28 own oil shares and industrial shares. So L intersection I, so the number of elements in L intersection I is 28. So we need to have that information before we proceed. Okay. The question is, how many members of the club own all three types of shares? You can't answer this question until you've drawn the necessary Venn diagram, and then you work out accordingly. So here, let's go. I'm going to transfer this on the next slide. And so let the Venn diagram here represent the three types of membership. Okay, so M for those who own mining shares, I for those who own industrial shares, and L for those who own oil shares. Okay, now making use of the information given, we know that that represents the universal set. We will leave out the rectangle because every member of the club owns at least a share, so they will all fall within these three circles. So we don't have actually to put the rectangle. The three circles altogether can represent the universal set. Okay, and so the shaded region must be the universal set, and from the information we are given, this is 133. So we can conclude that the number of elements in the universal set, which is the number of people in M union L union I, is 133. Okay, all right. What other information do we know? We know that the members that own mining shares, there are 96 of them. So the number of elements in the set M must be 96. The number of elements in the set L, those who own oil shares, that must be 70, I think, yes. And the number of members that own industrial shares, that is N of L, must be 70. So those are the cardinalities for membership. There are other pieces of information that we are given, including the fact that there are members who own both mining shares and oil shares, and so members with both mining and oil shares has been given to us, I believe, as 40. Okay, so we know that shaded region there is mining intersection oil must be 40. Similarly, mining intersection I, that means members who own both mining shares and industrial shares, I think this was 45. Okay, so that is 45. And members that own oil shares and industrial shares are, I think there were 28 of them. Okay, all right. So now what we're going to do is we will let the number of members that own the three types of shares, as the question is asking us. The question asks us to find the number of members who own all the three types of shares. Let that number of members be X. If we let that be the case, now we start reasoning backwards, and we will see, if we reason backwards, we can see that the number of members who own both mining and oil shares, we saw that mining and oil shares was 40. It means that if this part here is X, then the remaining part there in darkness there must be 40 minus X. Similarly, the number of members that own mining and industrial shares, that is 45. So if this part here is X, then the remaining part of this intersection here, this remaining part, must be 45 minus X. Okay, like that. And similarly, the number of members who own oil shares and industrial shares, I think there were 28 of them, and so whatever remains here, if that part is X, then what remains here must be 28 minus X. So we can put 28 minus X there, okay? And we can reason backwards to find what needs to be in these empty sections here, okay? So these are members who own mining shares but don't have industrial shares nor oil shares. This region here include members who have industrial shares but do not have mining nor oil shares. Similarly, this region here is for members who have oil shares but don't own any mining nor industrial shares. So let's start with this. If we were to find the number of members that own mining shares but don't have industrial and or oil shares, then we have to look at the total number of members that own mining shares, which we know is 96. And so I know 96, subtract this bit here, subtract that bit, and subtract that bit will give me the remainder, which is the number of members that don't own any of the other two shares. They only have mining shares, okay? So I'm going to find this number here by taking, and by the way, that will be the number of elements in M intersection I complement intersection L complement. In other words, outside L and outside I, okay? So let's find that out. Working with set M, all right? So we want that region that is shaded. It must be 96, which is the total of the circle in blue. Subtract 45 minus X, subtract X, subtract 40 minus X, as I have put there. If you simplify that, we should get 11 plus X. Please solve this and just confirm that you're getting 11 plus X. Okay, we can do the same with the number of members who own oil shares but neither mining nor industrial shares. Okay, and to do that, to find this region here, we have to take the total for oil. The total for oil is 70, and we have to subtract 40 minus X. We have to subtract X, and we have to subtract 28 minus X. Okay, if we do that, please try it out. If we do that, we should get 2 plus X as this region here. Okay, and if we do the same thing for this other region, which is the number of elements I intersection M complement intersection L complement, right? I intersection M complement, that means outside M and outside L, we get x minus 7. Please try it out and let's be sure you get the same thing. Okay? And so we will write x minus 7 there. So we can now conclude that if we added every element in these small parts here, we must add up to 133. So 11 plus x plus 45 minus x plus x minus 7 plus x plus 40 minus x plus 28 minus x plus 2 plus x. If we add all that, what we get must be 133. Okay, so I want to start by finding the area or the number of members in those outer regions. Okay, and so I'm going to add those three, and if you add 11 plus x minus 7 plus 2 plus x, we get 6 plus 3x. And if we add the remaining parts which are now inside there, those are the intersections, if we add all those together, that is going to be 45 plus x plus 40 minus x plus 28 minus x plus x. If we add all those together, please do it, you should get 113 minus 2x. And so the sum of this and that must add up to 133. If we do that, what do we get? Okay, so adding those, if we add those two together, we should end up with 133. And when I add that, I get 119 plus x is 133. And when you subtract that, x becomes 14. So this is to suggest that there are 14 members of the club, 14 out of the 133 members who own all the three types of shares. Okay, I can conclude that 14 members own all three types of shares, as the question requires us to do. Okay, I hope you understood this. If there's any part that you have not understood, let me know and I can take you through it a little bit more slower than this. Otherwise, let's move on. A few other questions that I want you to try out. These are important. What is the simplification of the following set? Well, what is the set A intersection A complement? Members that are both in A and are not in A. How many members are that? Of course, this is the null set. It's not possible that you are in and you are also outside A. Okay, so that would be a null set. And in the same way, please try the others and let's see what you get. We can discuss your solutions. Okay, that's problem number 6. And here is problem number 7, again, that I want you to try out. Consider the universal set of elements x such that the elements are positive integers and are less than 10. So they are positive integers that are less than or equal to 10. And the set P is the set containing 2, 3, 5, and 7, while set Q contains 2, 4, 6, and 8. Show these sets on a Venn diagram. And part B, find the number of elements in the set P complement. Find the number of elements in the set P intersection Q. Find the power of the set. That means listing the subsets. How many subsets are in P intersection Q? That means the power of the set. And now how many? This is referring to the number of subsets. So here you are listing the subsets, and here you are counting the number of subsets in the set P union Q. Okay? You do not need to do much calculation. You don't need to list out the elements. You should be able to get the number of subsets here without necessarily having to list out the elements. I hope you can do that. And part B says a number is randomly selected from the universal set. Find the probability that the number is not an element of the set P. Try this question out and let me know what you come up with as a solution. And this brings us to the end of this video. As I have said, please send any question that you would like us to go through regarding this exercise or regarding this lesson, regarding Venn diagrams. We will be able to go through that together. Also, if you try out a question and you find you're not able to complete it, and you want to ask me a question regarding it, let me know and we can do that together. Otherwise, in the next video, we will be looking at the number sets, okay? Please check out the comment section. I will put a link to workbook number 4 so that you can try out the questions in that workbook. I believe I also intend to put another worksheet that will contain the extended type of questions for you to try out. I'll try to put the questions together with the answers if possible. Otherwise, I'll put the questions and you can always ask me individually and I will be able to solve those questions for you. All right? Thank you very much. I'll see you in the next video.